Hi guys, and welcome to part 2 of episode 2 of my PIC and assembly language lecture series. So in this series we'll be working with the exercise for the previous video. Essentially we're going to have the blinking LEDs, and we'll take what we've learned from the previous videos, and from time to time we'll be referring to the datasheet, which was the highlight of the previous lesson. So let's proceed. Let's open up our MPLAB X. We're now at our MPLAB X IDE. Before we start, I'd like to inform you with something trivial but quite important if you miss this out sometimes. So in the tools options, you have a window there. Options, go to miscellaneous, and then files, choose the ASM file, and make sure you are at ASM file, this one, text x-asm. So that's just a tip that I would like to share first before we start. So this makes sure that all .asm file extensions are opened as actual assembly language module files. So just press OK, and that's it. Let's create a new project, and let's choose standalone project. And once again, we choose the mid-range family and PIC 16 F877A, and go next, and let's choose simulator here and the ASM compiler. Let's name this exercise 02, and it's set as main project here. So now let's add a source file. Let's call it main.asm, and click finish. As usual, we'll be writing our header, just to make sure we are doing things with documentation. So in this exercise, we'll be working with a program that blinks the LEDs. Let's call this Blinky, and it blinks the LEDs of a certain circuit with PIC 16 F877A at port A. So that's it. Then we put in the author. You may put your name in your own work. So for mine, I'll put my name and the date. So today's 11, and then let's end our header. That's it. Now, as we have discussed in my previous videos, in the reference we had the PIC 16 F877A reference. So as you can see here, we had some memory organization here, and it is stored as there are some relevant data in here. Now what we have to do is try to figure out our algorithm. So it's really very simple. First, we have to set our region though. So let's use that code. We actually had that from our previous project, so it's not going to be really difficult. You can just copy and paste it. And then we would like to start our program. So let's start our program there. So what's interesting is we now need to make sure port A is defined as a digital pin. So looking back at our documentation, before we make sure that port A is digital, we must have to make sure first that all the values in port A are 0. So as we've checked from here, port A is in bank 1 because this column is port A is in bank 0. So port A at address 05H is at bank 0. So we like to make sure port A as a register with 8 bits must have all of its bits with a value of 0. So let's go to bank 0 first. In order to do that, it's very simple really. You just need to make sure the status here is, if we go back a bit, the status RP1 and RP0 or status 6 and status 5 are both 0. So if RP1 RP0 of status register is 0, then you are in bank 0. To do that, we must first see where status is located. So status is located at 03H. So it would be very difficult if we have to memorize that status is at 03H. So there is a macro system in assembly where you can make a constant literal that says, okay, if you write status, point it to 03H. So this is what we have here. I'm gonna copy this code here and I'm gonna transfer it here in the top portion. So what it does is it makes sure that we have mapped the register names, for example status, to 03H, because as you can see here in our datasheet, status is 03H. So if we have status is at 3, we also have port A at 5 and adcon 1 at 9FH, but it's in bank 1, and also in bank 1 tris A at 85. As you can see here, tris A is at 85. Let's note this is in bank 1 and this one also in bank 1. However, these two are in bank 0 of the PIC microcontroller. So that's it. These are the file map here, and then we proceed with making sure that we have the algorithm correct. So we move to bank 0. There we go. BCF, you must remember this is an instruction. So BCF, it was written here in the instruction summary where it is a bit clear F. So BCF bit clear F, where it clears a certain bit from inside a byte of a certain F register, where that certain F register in our case here is status located at 03H. So instead of writing BCF03H and then the address of RPO, by the way, we have not added it yet, so we have to add them. So the address of RPO within status is this. So actually you have to note that RPO and RP1 is inside the status register, and RPO is the 5th bit, and RP1 is the 6th bit. So it would be easier if we would write BCF status and the RPO bit, rather than writing BCF bit clear F 03H comma 05H. That would be very hard to read and understand. So this is how we make things easy. Okay, let's proceed. Now we have transferred to bank 0. Our goal here is to make sure port A is cleared. So the command for that is quite simple. It's just a clear F command, an instruction that clears a certain F register. In this case, since port A is in bank 1, we must first transfer to bank, in this case, since port A is in bank 0, we transfer to bank 0 here, transfer to bank 0, and then we clear all the bits inside the port A register. So it would clear all the output data latches. Now we need to transfer to bank 1. Going back to our datasheet, bank 1 is at RPO RP1 1. So as you can see here in the memory organization, RP1 is 0, RPO is 1. So since we already had both RP1 and RPO 0, we only need to change RPO into 1 in order to go to bank 1. So essentially we can summarize that we only need to change RPO. So in order to change RPO into a value of 1, we need to use bitsetf command here in the instructions summary. So in the later part of this video, I'm no longer going to go back and forth with the datasheet, but at this moment I think it's well worth the effort so that you can understand easily. So bitsetf, we're going to use this on the status register F and bit RPO. So that's it. Going back here, we bitsetf RPO. That's it. Now this selects bank 1. So we can assume from here that RP1 is 0. So it's just like RP0 is equal to 0. And here RP1 is equal to 0, and a bit around here we have RPO is equal to 1. So it's rather very easy to understand, so not very difficult at all. So this is bit set, this is bit clear. Now we have to make sure that all pins are configured as digital pins. That's it. We have to make sure that all pins within port A are digital. Why? Because essentially we have to make so going back to the IO, the IO ports summary, you can see here that in their example they actually change port A to make sure that all pins are digital. Why? Because port A is a shared port, whereby in the specification in the in this specification for the PIC that we're using, port A here is also an analog input. So as you can see here, RA1 AN1, RA0 AN0. So going back here, let's make sure that port A is digital. So the command for that is this one. It moves the value 0x06 or 6 into register W, and whatever is in register W, it transfers to ADCON 1. Where is ADCON 1? That is at address 90FH of bank 1. So that is why we transferred to bank 1 here. We transferred to bank 1 before modifying the value of what is inside in ADCON 1, which is at address 9FH. So I hope that's clear. Now, in order to blink, we must first perhaps make sure that after our pin is digital, we must make sure that our pin is an output pin and not an input pin. Digital output pin and not a digital input pin. To make sure that the direction is set, we need to use the TRIS-A register for port A. So let's check the TRIS-A register, and in order to set the direction to output, we must set the TRIS-A to 0. So simply that would mean that we could move a value to the working register that is 0 and then move whatever is in the working register to TRIS-A. So the command for that is quite simple. Here we have a value of 0 and we move it to register W, or the working register, and then we move whatever is in the working register to TRIS-A. So that sets all. After setting TRIS-A to 0 and making sure that port A is an output pin, we'll then go back again to bank 0 in order to give a value to port A. As I said, port A is in bank 0, so before we can modify port A, we need to go back to bank 0. So I think that's pretty clear already. Going back to bank 0 would only require copy pasting the initial code we had and making sure that we clear status registers, port pin RP0 and RP1, making sure they are both 0. So you can just copy paste this block of code here. So let's use that. So we have comments. So now we're at bank 0. Then this is where the fun starts. What we have to do now is put a value into port A. So since we are blinking the entire port A, that means that there are actually 6 pins in port A. Then we would like to light them up first, then turn them off, then light them up in a looping way. So in order to do that, we need to create a loop. But before that, the code to start the lighting or begin the lighting is this one. I think you should have guessed it by now, but it's very simple. You set all the bits of port A into 1. That would mean a high volt and a logic high. So first we set FF, which is a binary for 8 ones. Which first we set the working register to FF, which is a hexadecimal for 8 ones. So we move them to the working register, and whatever is inside the working register, move them to port A. So that's it. Very simple. That would set port A into with values of high logic high. After a certain time, we make sure that we set we set the values of port A to 0 once again, and then we loop back to the start. Okay, here we go, and end our program. So I think this should be pretty understandable. We can actually simulate it if this builds correctly. So let's try to build it, our code. So it's not building because we are not. Okay, so I have made a huge mistake here. This is supposed to be a comment. So this is something that's brought from C and C++ and other programming languages that use that kind of commenting system. So I'm very sorry about it. So we have completed the compilation, and just like before, we can now simulate our program. So let's debug. Okay, so there's something wrong with our comments, by the way. This one turns on, turn on all LEDs, turn on all pins on port A. So that should simplify our comment. Okay. And this one here, let's just copy this and make sure we are turn off all LEDs on port A. So that's it. We turn on, turn off, then go back to turning on. Then we debug the main project. If we go to pause, then reset. So now let's try to trace our program and see what happens. In order to do that, let's go back to debug. Oh no, let's go to window and into debugging. Into PIC. Let's go to window and let's go to PIC memory views and check on SFR. So I think for this window it would be better if it's in the side. So no, this is too small an area for this window. So let's make sure we have a great, okay, this is probably the best place for this. I think this is it. Okay, that's it. Better place for this one. So now that SFR is open, let's reset and try to step over one by one. You should also take a look on this. This is the program counter, this is the status flag, and the bank. So this is very important. So let's try to step over one code at a time. So check status here. As you can see, this is status, and if you could step over once more, we are now at bank 0. And then let's clear port A, although port A here is already cleared. That's just for making sure that we're doing things properly. We have to clear them so that they are defined, so that we know that we're working on a clean system. Then we go to bank 1, so now the bank has changed to bank 1, and then we move a value to register W, or the working register, that is 6. So if we check W reg here, it's 6, and then we once again step over and we move 6 to adcon 1. So if you can check adcon 1 here, this is adcon 0, this is adcon 1, that is already 6, and then we move a value of 0 to W reg. So now W reg is 0 and we are at line 8. And then we step over once again to move all these zeros into trace A. So if we see here, trace A is at 63. Once we step over, trace A is now 0. So next is we transfer to bank 0. So check it out, status has changed, and then we move another line again. Now we are actually at bank 0, and then at this point we are now at bank 0. We can now edit the value of port A. So first we move all ones into the working register. As you can see here, the working register is now all ones. That would mean a logic high, and we move those all ones into port A. As you can see here, port A is 0. Now port A is 63. So why do you think that port A is 63 and not 0xFF? To answer that question is simply because the last 2 bits in port A is not defined by the microcontroller. So every time you read them, their values will be 0, regardless if you wrote 1 to them. So the system really doesn't care if you write 0xFF. Only 63 would remain, because only bits 0 to 5 would be changed, and 6 and 7 would remain 0. So that's it. That's a very simple application. That's a very simple explanation for that there. So what we do next is move WF. Move the value of 0 once again to port A in order to turn off all pins on port A. In order to do that, we move 0 to register W, and whatever is in register W we move to port A. So that's it. Very simple. And once again we go back to start, turn it on, and as you can see here, port A is now going back to 0 and 1 back and forth as I click on the simulator here. So that's it. That's how simple this is. So there is one problem with our program though. Although we already got the algorithm correct, there is just one problem. How fast do you want your blinking to happen? Let us remember, here in the device configuration, we can actually in the simulator set the oscillator options. This microcontroller runs from DC up to 20 megahertz, as was specified in the datasheet. So what if we intend to run this system at 4 megahertz? This one. So in order to run the system at 4 megahertz, we'd need a circuit that I have talked about earlier. At 4 megahertz, these instructions would be given at least around 1/4 millionth of a second. These instructions, each instruction would run 1/4 millionth of a second. So that would be very fast. you wouldn't even notice these things blinking because they would just be showing as lit. So in order to make sure we see the blinking, we have to slow the algorithm. To do that, there is what we call delays. Delays are something like do nothing, just delay the time. We need to put a delay here as our first. Let's stop this debug, and we need to put another delay here. So essentially what happens is that there is a delay after turning on and before turning off, and after turning off and before turning on back again. So in order to work with delays, there's a very simple set of instructions that actually allow it. But let me copy this block of code I have in my library, and I will explain it. Here we go. This is our first delay, and for our second delay, here we go. So what happens with these delays? Before explaining it, we need to add the constants for first and second delay. Okay, we add them here. This is count 1, which is a constant that we've made, and look at this. It is a constant pointing at address 20H, and count 2, which is pointing at 21H. So what is at 20H and 21H? These are general purpose registers. Looking back at our datasheet, we need a register that will hold a value for us comparable to variables in regular programming languages. So it's easy to spot because here in the memory organization, the unbanked 0, as you can see here, unbanked 0, there is a general purpose register that has 96 bytes of free space from 20H to 70FH. So from 20H to 70FH, you can use that for any purpose you may want. So I have decided to put a counter inside 20H and 21H. So this is our variable counter. This is it. Count 1 for the first loop and count 2 for the second loop. Just remember, those things are at bank 0, so we need to specify that we are at bank 0. However, since we are already at bank 0 due to this command, because port A is also at bank 0, we can safely assume that at the point we enter count 1 and count 2 here, at the point we define them and we use them, we are already at bank 0. So what happens with our delay code? As it starts from here, first we make sure that our working register has a value of 255, or the highest value that can be stored in an 8-bit register. Then we move the 255 value to count 1 and then to count 2. So that is just saying count 1 is equal to 255 and count 2 is equal to 255. Then we use this interesting command. It's an instruction, DECFSZ. You might wonder what that means, but it's clearly defined in the instructions summary. So if we go here, this means decrement F else skip if 0. So it's really very simple. First, it decrements the value of count f by it decrements count 1, which is our f, register f, count 1, and decrement 1 by it. So that's it. This is it. Decrement f with d and skip if 0. So what happens then is that if the count 1 is now 0, it will skip this line here and it will go directly to this line here. However, if this line here, after decrementing count 1, which we've set to 255 earlier, is still not 0, it will go back to loop 1. So it will not skip this line. So what happens is that there is a loop that happens from here to here, and then it just loops like that for 255 times. And after that, when it reaches 0, it goes here. So as you can see, count 2 is still 255. That would mean we'd be looping back again to this part, and it will go back here. So what happens essentially is that this delay counts them down from 255 to 0 255 times. So that's what happens. You can observe the behavior in a much clearer way later once we start debugging this program or simulating this program. So this is the same code as we had earlier, and then this is just another set of delay which uses loop 2. So we use another label here because we don't want to be going back to this loop here. We just want a self-contained loop in here. So let's start simulating this program. However, in order to show you the behavior more clearly, let me change this to 5, so that instead of from 0 to 255, we'll only be dealing from 0 to 5. So there we have 2 delays, and we've changed them to 5. Let's see what happens. Let's reset. So first we're at this point. Let's move. Let's put a breakpoint here. And let's put a breakpoint here. And let's observe what happens. Also, in addition, let's go to the file register. Was this the correct register? Let's try. Let's continue. So we're now at this point. So the breakpoint is actually something that cuts the simulation at a certain point if you just click the continue command. So we're now at this point, and then we also add a breakpoint here. So what happens is it will decrement. First, let's find 20H. So where is 20H? So it's gonna very hard to see things from here, but I think it's in 20. Let's use a different view. Format symbol. So let's check out 20. As you can see, 20 and 21 are now equal to 5. That's it. We've set both of them. with these commands. Okay, and now we try to continue. Now this just loops to itself, because first it decreases this and it's still not 0, so it goes back here until it reaches 0. But what's interesting is that it goes back here, and now it decreases this to 0. This decreases this by 4. So what happened here is that since we've already reached beyond 0 and you still continue to decrease the value by 1, that would mean that you've lower than 0, you'd go back to 255. So that's how registers are programmed. If you're less than 0, then you go back to 255. So this is why this happens 255 times. If we play this happens 255 times, and then if this reaches, for example, to, if we modify this here to 1, and then we go back once again, this is reduced to 3, 21, this is count 1. As you can see here, we define count 1 as register 21. Then this one again turns to 255. So that means we have 255 255s. That's 255 times 255 instructions to delay the running of the program. So that would cause a delay, and then that would look like as if that port A is lit during that time. So we pause this program and we return it to its original 0xFF value, which is equal to 255. So in order to test if we really had our program correct, I have developed a very simple circuit using Proteus. So in our exercise directory, there is a very simple circuit here in Proteus, as I said in the beginning. Let's double click this IC and let's point it to this, to PIC, and then vid02 x02 distribute, develop, debug, and this one. Let's click OK and let's simulate. As you can see here, the pins are blinking, and you can see some of the variables here. Trace A is all 0, that would mean output, and port A are all 1s. It would blink from 1 to 0. So that's a very simple demonstration of our blinking LED exercise. In our future demonstrations, we would use an actual hardware and PIC16 F8778A PIC to test our code if it really acts as intended in real life. Thank you for watching for our second episode of the PIC and Assembly Language lecture series. By the way, if you have any suggestions or comments, please leave it in the comments section below. Thank you.